You take any crazy idea. I don't know, it's hard to make up a very crazy one day, witches or something like that, and you tell about what people used to believe in witches, and of course nobody believes in witches now, and you say, how could they believe in witches? Then you turn around and you say, let's see, what witches do we believe in now? What ceremonies do we do? Every morning we brush our teeth. What is the evidence that the brushing the teeth does us any good in cavities? So you start wondering, are we all, imagine as the Earth turns on the orbit, there's an edge between light and dark. And along that edge, all the people along that edge were doing the same ritual for no good reason. Just like in the Middle Ages, they had other rituals. And you try to picture this perpetual line of toothbrushes going around the Earth. It's to take the world from another point of view. Now, it may well be that brushing teeth is a very good thing because it gets rid of cavities, and you can find out whether it does or it doesn't by trying to find out. Now, you can ask your dentist, and he says, of course. And you say, how about evidence? I have not found the evidence from dentists because they just learned it in school. Now, I'm not trying to argue that it's good or bad to brush teeth. What I'm trying to argue for is to think about things from a new point of view. I have had in my life a number of pleasant experiences. The earliest one, when I was a kid, I invented a problem for myself, the sum of the powers of the integers. And in trying to get the formula for it, I developed a certain set of numbers formula for which I couldn't get. And I discovered later that those were known as the Bernoulli numbers, and discovered in 1739. So I was up to 1739 when I was about 14, you see. And then a little later, I discovered something. I find out invented a thing called, which we now call operator calculus. And that was invented in 1890 something. You see, I was inventing things that came later and later. But the moment when I began to realize that I was now working on something new was when I read about quantum electrodynamics at the time. And I read a book and I learned about it. For example, I read Dirac's book. And he had these problems that nobody knew how to solve. They were described there. I couldn't understand the book very well because I really wasn't up to it. But there, in the last paragraph at the end of the book, it said, some new ideas are here needed. And so there I was. Some new ideas were needed. Okay, so I started to think of new ideas.
Richard Feynman, Nobel Prize winner, and his son Carl stepped gingerly down the wet cobbles of Millbank, high in the Yorkshire Pennines. Feynman, professor of physics at the California Institute of Technology, retreats to this remote village near his wife's home for a special purpose. It's here he finds the time and solitude to sift the ideas that have made him the most feared and original mind in modern physics. Feynman is in the forefront of one of the oldest and most intriguing games of hide-and-seek in science, finding the ultimate constituents of the world. In this search, Feynman is a celebrated maverick who was encouraged by his father, a New York clothing salesman, to confront conventional wisdom.
One Sunday, all the kids were all walking in little parties with their fathers in the woods. Then the next Monday, we were playing in a field, and kid said to me, say, what's that bird? What's the name of it? Do you know the name of that bird? I says, I have the slightest idea. He said, well, it's a brown-throated thrush. He says, your father doesn't teach you anything. But my father had already taught me about the names of birds. Once we walked and he says, that's a brown-throated thrush. He says, know what the name of that bird is? A brown-throated thrush. In German, it's called a Flügelflügel. In Chinese, it's called a Qinglongtong. In Japanese, a Tohatahara, and so on. And when you know all the names in every language of that bird, you know nothing, but absolutely nothing about the bird. And then we would go on and talk about the pecking and the feathers. So I had learned already that names don't constitute knowledge. It's knowing the name of something. That's caused me a certain trouble since, because I refuse to learn the name of anything. So when someone comes in and says, You got any explanation for the Fitz-Cronin experiment? I says, what's that? He says, you know, that the long-lived K meson disintegrates into 2 pies. Oh, yes, now I know. But I never know the names of things. What he forgot to tell me was that knowing the names of things is useful if you want to talk to somebody else. So you tell them what you're talking about.
But the basic principle of knowing about something rather than just knowing its name is something that you stuck to, is it?
Yes, of course. You have to learn. These are kind of disciplines in the field of science that you have to learn. That to know when you know and when you don't know, and what it is you know and what it is you don't know. And it's you got to be very careful not to confuse yourself.
How else did he try and
progress?
mold your methods of thinking, the way you looked at the world?
Well, we had a lot of little games, like he would say at the dinner table. He'd think of some little problem, and he'd say, suppose you were a Martian, we were Martians, and we came down to this Earth, and we'd look at it from the outside. And that, I can't explain exactly what he meant, but there's a way of looking something anew, as if you never saw it before, for the first time, and asking questions about it as if you were different. For instance, if you would ask, later I did some little amusing research for a paper in college on sleep, but it started with a question of his kind. Suppose you were a Martian who never slept. They didn't have sleep. You didn't have to sleep. And you came down to this Earth and you saw these people who had this funny property that every day for a certain amount of time had to lie down and become unconscious. And then the natural question would be, how does it feel to get unconscious? What happens to you? Ideas run along and suddenly they stop, or do they just run more and more slowly? But what happens to your ideas? How does it feel to become unconscious? So I tried to answer the question. What happens when you become unconscious?
But you find that these days, you still, when you're faced with a particularly difficult problem, when you're absolutely stuck, you tend to say, let's look at it like a Martian would look at it. And
sometimes. There are lots of things that people did. For example, Maxwell put the equations together. The Faraday, he formulated the equations mathematically with some model in his head. And then Dirac got his answer by just writing and guessing an equation. And other people got their answer, like in relativity, got the idea by looking at principles of symmetry. Now, all these methods, and Heisenberg got his quantum mechanics by thinking only talk about the things that you can measure. Now, all of these ideas, we should only talk about things that we can measure. Try to define things in terms of only things you can measure. Or let's formulate the equation mathematically. Or let's guess the equation. Or all these things are tried all the time. Look for symmetries. All that stuff is tried. All that stuff, when we're going against the problem, we do all that. That's very useful. But we all know that. That's what we learn in the physics classes, how to do that. But the new problem, where we're stuck because all those methods don't work. If any of those methods would have worked, we would have gone through there. So when we get stuck in a certain place, it's a place where history will not repeat herself. And that's makes it even more exciting, because whatever we're going to look at the method and the trick and the way it's going to look is going to be very different than anything that we've seen before, because we've used all the methods from before. So, therefore, a thing like the history of the idea is an accident of how things actually happen. And if I want to turn the history around to try to get a new way of looking at it, it doesn't make any difference. I don't care. The only thing that the real test in physics is experiment, and history is fundamentally irrelevant.
The most enduring legacy from his father was not just learning to question the physical world, but an enthusiasm for the inquiry, which at 54 Feynman still shares today.
It has to do with curiosity. It has to do with people wondering what makes something do something. And then to discover that if you try to get answers, that they're related to each other. That things that make the wind make the waves, and the motion of water is like the motion of air, is like the motion of sand. The fact that things have common features turns out more and more universal. What we're looking for is how everything works, and how everything is, what makes everything work. And what happens first in the history is we discover the things that are on the face of it obvious. And then gradually we ask more questions, and then we dig in a little deeper to things that we can just make. We need to do a little more complicated experiment to find out about it. But it's a curiosity as to where we are, what we are. It's very much more exciting to discover we're on a ball, half of it sticking upside down. It's spinning around in space. There's a mysterious force which holds us on. It's going around a great big glob of gas that's burning by a fueled by a fire that's completely different than the fire, any fire we can make. Well, now we can make that fire, nuclear fire. No, but that's a much more exciting story to many people than the tales which other people used to make up who worried about the universe, that we were living on the back of a turtle or something like that. They were wonderful stories, but the truth is so much more remarkable. And so what's the pleasure in physics is that, to me, is that as it's revealed, the truth is so remarkable, so amazing. And I have this disease, and many other people who have studied far enough to begin to understand a little of how things work are fascinated by it. And this fascination drives them on to such an extent that they've been able to convince governments and so on to keep supporting them in this investigation that the race is making into its own environment.
As a theoretical physicist, Feynman doesn't have a laboratory, and he finds family relaxation helps him to concentrate. In recent years, he's been concerned with the long-asked, almost childlike question, what are things really made of? What makes up the world we see around us? Have we at last come to the foundation stone from which we can make anything? A tree, a human being? Or must we go on looking at smaller and smaller pieces and going deeper and deeper into a bottomless pit? Feynman is trying to knit together our scattered knowledge of the smallest pieces of matter to see whether they fit a pattern. The problem, although fundamentally important to all branches of science, seems far removed from everyday reality.
The world is strange. The whole universe is very strange. But see, when you look at the details and you find out that the rules are very simple of the game, the mechanical rules by which you can figure out exactly what's going to happen when the situation is simple. It's again this chess game business. If you were in just a corner where only a few pieces are involved, you can work out exactly what's going to happen. And you could always do that when there's only a few pieces. And so you know you understand it. And yet, in the real game, it's so many pieces you can't figure out what's going to happen. So there was a kind of hierarchy of different complexities. It's hard to believe. It's incredible. In fact, most people don't believe that the behavior of, say, me, one yak, and you nodding and all this stuff is the result of lots and lots of atoms all obeying these very simple rules. Come out that it evolves into such a creature that a billion years of life with its experiences has produced a thing with prongs that stick out like this and so on. There's such a lot in the world, there's so much distance between the fundamental rules and the final phenomena that it's almost unbelievable that the final variety of phenomena can come from such a steady operation of such simple rules.
But you've had to build the most complex scaffolding to find out the simple rules.
But it is not complicated. It's just a lot of it. And if you'd start at the beginning, which nobody wants to do, I mean, you come in to me now in an interview and you're asking me about the latest discoveries that have been made. Nobody ever asks about a simple, ordinary phenomenon in the street. Like, what about those colors? Or something like that. We have a nice interview, explain all about the colors. Butterfly wings, whole big deal. You don't care about that. You want the big final result. So then it's going to be complicated because I am at the end of 400 years, a very effective method of finding things out about the world.
In the search for the ground rules of the physical world, John Dalton worked out a comprehensive explanation over 150 years ago. He assumed that everything we see is made out of tiny atoms, that they're immutable and indestructible, and that atoms of different chemical elements like lead or copper have different weights. Too small to be observed, the atoms combine with each other to form complicated molecules, and vast collections of these molecules are recognizable to us as tables, trees, or whatever. But in the final analysis, atoms were to be the smallest constituents of matter, ultimate and unchangeable. At the turn of the century, we evolved our present picture of the atom, light electrons surrounding a heavy central core or nucleus. Once the atom was shown to be destructible, attention turned to the nucleus, and during the 30s it was found that bombarding one nucleus with another led to a release of energy and the breaking up of the nuclei. This process, which takes place in nuclear accelerators, is photographed in a liquid bubble chamber.
You take a liquid hydrogen or some other liquid, and expand it so that it's ready to boil. Your low temperature and you decrease the pressure, it's ready to boil, and it has to form bubbles somewhere. And any little piece of dirt or any little disturbance, it'll form a bubble. In that condition, if a particle comes flying through from some machine, it leaves a track. It tears up the atoms along where electrons are knocked off the atoms along its track. And we can't see that. But when the gas tries to expand, when the liquid tries to boil, the bubbles form around these charged particles which are left. So it leaves a string of bubbles are then formed. Then you can take a picture of the bubbles. So simplest picture would be if you had a machine that made fast particles. Particle would go through, and you see a string of bubbles. But if the particle on the way through hit the nucleus of another atom, then you see a string of bubbles and a kind of a Y if it made its recoil plus some other thing. And instead of a Y, you may see more complicated tracks, 3 or 4 coming out, and then one of them going along and going into 2. Then you know that some particle went along and disintegrated. Now, these things are going nearly at the speed of light. And so if you can see a short distance, a few centimeters, that corresponds to a 1/10 of a billionth of a second. That is, if a track comes out, goes along here, and then bifurcates into 2, you know you made a particle which disintegrated into 2 in less than a 10 billionth of a second. So you see, it's not very difficult to find out about these things with clever techniques.
Since the war, with evidence from bubble chamber photographs like this, physicists have explored the nucleus of the atom. The results have been spectacular and confusing. The harder the nuclei were bombarded against each other, the more they disintegrated into even tinier particles until literally hundreds were known. In the last 10 years, some order has been made out of seeming chaos by arranging the particles into patterns. Each pattern has 8 or 10 members, related by nuclear properties like spin and mass. To the physicist, patterns like this imply the possibility of even smaller particles, not yet identified but already named. The key to the question of what makes up the physical world, then, lies in the understanding of the nature of these nuclear patterns.
We're getting close because we have a number of little theories by which we can understand these patterns. One picture which describes what particles you're going to find rather well is that all these particles are made out of something else which we happen to call quarks. And our quark is an object which comes in 3 varieties. It's either an A-type, B-type, or C-type quark, okay? And that the particles that we find are of 2 big classes. And one class we can understand as being made out of 3 quarks. And depending on the different proportions, how many A's, B's, and C's, and how they're moving around each other, if we count how many states we would get from putting 3 objects together, it could be made in so many ways, 27 different ways, each one being 3. We find groups of particles in groups of 27 analogously, and so on. A little more complicated, but it's more subtle, but it's like that. And then when we allow for their motion around each other, we find the higher energy states analogous to the way that we ought to get. And even semi-quantitatively, there seems to be a relation between the states, the rates at which one turn into another. So it looks like they're made out of just 3 quarks. Then there's this other class of particles which are called mesons. The first class were called baryons. The words aren't going to do you any good. But the other class of mesons we have to understand as being made of a quark, 1 quark, and 1 antiquark. An antiquark is a negative particle with all the numbers, all the charge properties, the exact opposite of a quark. When we make a quark and an antiquark, put those together, we understand the meson states. Put 3 quarks together, we understand all the others. So we have made a really great progress in analyzing these patterns. So much so that it looks very much as if, to me at least, that we're very close to understanding this part of physics, this strongly interacting system.
But what's the main barrier still to?
Well, the quarks have... Well, the main barrier is we don't understand it quantitatively. We don't know exactly the laws. I mean, we do things like I'm just talking to you, only a little bit more carefully, counting how many states we should get and so on, but we don't know exactly how they move and exactly what holds them together and so on and so on. Also, there are a number of paradoxes with this quark picture. This picture helps to give us the behavior at low energies of what kinds of particles to expect. But then you'd expect that a particle would be made out of only 3 parts. But we've done some experiments at very high energy, hitting a proton with an electron, which can only be interpreted by supposing that the number of particles inside is really infinite, if there are particles inside. It can't be done with just 3. You can calculate, it doesn't come out right. So there's a difficulty. Furthermore, The idea that there just be three particles is contradictory to the ideas of relativity and so on, which imply the existence of particles and antiparticles. And when there are three, there should be possible for the forces to produce pairs of particle-antiparticle in various numbers. So there should be not just three, but many more. So the infinity is not a paradox by itself. The three is more of a paradox. Why is it so simple? Why can we get away and understand so much with just three when there should be an infinite number probably in there, both theoretically and experimentally? Another thing that's a little technical but very paradoxical is that we had a rule back for atoms that no two electrons can occupy the same state. It's called the exclusion principle. And we thought we understood that that was necessary according to quantum mechanics and relativity. It has to be. And with the quarks, we find the exact opposite rule. Two particles tend to occupy the same state. The exact opposite. It seems to be contradictory with principles. There are ways of escaping this all the time, only by complicating the picture. But the simplest picture, just three, which explains everything, is self-contradictory. Furthermore, some people suppose that maybe these quarks could come apart. That would mean the prediction of new states, which consists of only one quark, say. If there were such a state, it would have to have a charge of 1/3 normal charges of our objects, for example, or 2/3. And we don't find experimentally any such particles. Now, everybody's looking for them. But it looks as if they exist at all, they have to be extremely heavy. Then the problem is, very good, if they're extremely heavy, how, compared to a proton, say, how is it when you put three of them together, you get a light object that's not heavy, like the proton? There are technical ways of arranging it, but they're always complicated. The situation is, as it always is when we're near the answer. It looks much simpler than it has any right to be. And we have to understand that simplicity and why we think it must be more complicated. Our minds are complicated somehow. Just like the orbits of the planets, which were supposed to be circles, which looked simple. Then they were experimentally, they weren't circles. So they made circles on circles on circles on circles, got more and more complicated. Turned out it was really much simpler. It was a force inverse is the square of the distance, which made ellipses and so on. But a different way of formulating entirely, which was beautiful. So now we have our wheels within wheels. It looks simple. Nature is no doubt simpler than all our thoughts about it now. And the question is, what way do we have to think about it so that we understand its simplicity? That's where we stand now.
On holiday in the Pennines, Richard Feynman is paid a neighbourly visit by Yorkshireman Sir Fred Hoyle, the astronomer, cosmologist and science fiction writer. At first sight, there seems little in common between the study of galaxies and nebulae billions of miles in diameter and millions of light years old, and nuclear physics, where particles exist for only a millionth of a second. But the formation of stars and galaxies is determined on a massive scale by the behaviour of the very nuclear particles Feynman studies. Hoyle and Feynman share an interest in the foundations of physics, and exchanging ideas in the local pub is always as profitable as it is enjoyable.
And you agree that the quasars are in real trouble, that the very big redshifts...
I think so. I've had this uneasy feeling now for about 5 years. It looked crazy for a while, but it's like piling up of evidence all the time this way.
Each one makes a new problem.
Yeah.
Every piece of evidence is the same problem in the same sense. If there were any cause for a redshift as big as that, other than recession, we'd be all right.
That's right.
But in the present physical laws, there doesn't seem to be any place for such a redshift.
That's good. That
That's
fits.
good.
Right. That won't fail.
And at the same time, the same kind of laws predict the kind of peculiar phenomenon of black holes, which really confusing.
Yeah.
And it could be that either the gravity is wrong or one of the physical laws are wrong, too. Some physical law that's involved.
But I'm not arguing at the moment that the physical laws are wrong. I mean, you would agree that one has to push it through along these lines.
Yeah, the best way to progress, I always think maybe, is to try to be as conservative. That's what Wheeler always said. To try to be as conservative about the physical laws as possible in explaining the phenomenon. And if you continuously fail, then you gradually realize you got to change something. But if you start out by saying got to change something, there's so many ways of changing it, and you don't know how it's most likely you don't have to change anything. Most of the time we succeed ultimately in explaining these damn things in terms of the known laws, but it's the cases that fail are the interesting ones.
Yeah. Yeah, it's like the old story, isn't it? The chap with the under the single lamp in the street.
Yes, that's right.
Where a passerby says, "What are you looking for?" He says, "I'm looking for my key," and they search for it for a few minutes. And at the end of these minutes, the passerby said, "Are you sure you lost it here?" And the man said, "Not at all, but unless I lost it here, I'll never find it."
Because the light's better here.
Yeah.
Yeah, we work where the light's better.
Yeah.
Once I was thinking by analogy that there was a time in the 1900s when the thought that the properties of substances were not physics. For example, they would be numbers. We would find a series of numbers. The index of refraction, that was physics. But the number for the index, that glass had an index of 1.543 and so on, that salt had another index, that those numbers, the properties of substances, would come from chemistry or something. But that it was that time, it was considered a different branch. Then when the quantum mechanical understanding of the atoms was evolved, then we could calculate all these properties, and we realized that all these numbers were really part of physics. And so properties of substances became a branch of physics, whereas previously it was a sort of chemical branch. Then I wondered by analogy, I always worked by analogy, what today do we not consider part of physics, which may ultimately be part of physics?
I see.
And I realized immediately something. We consider, at the present moment, most people consider that we study the laws of physics, that is how things go, given a certain condition, how the things behave after that. But how did they get into that condition is considered another problem. In other words,
boundary conditions.
Right, boundary conditions. We are given the
yeah,
conditions,
yeah,
the circumstances,
yeah.
and then it evolves from there
yeah,
according to physical
yeah,
laws. We're
yeah.
studying the laws.
Yeah.
It's as though we were doing a chess game again, and we're working on the rules, but we're not worrying about how the pieces are supposed to be set up on the board in the first place. That's not our business. That's the business of history, how the world evolved. Astronomical history, history of cosmology, how the universe exploded or the steady state or whatever it was. It's not our business. It's interesting that in many other sciences, there's a historical question, like in geology, the question, how did the Earth evolve to the present condition? In biology, how did the various species evolve to get to be the way they are? But the one field which has not admitted any evolutionary question is physics. Here are the laws, we say. Here are the laws today. How did they get that way in time? We don't even think of it that way. We think of, well, that is that way from forever. It's always been like that, the same laws, and we try to explain the universe that way. So it might turn out that they're not the same all the time, and that there is a historical evolutionary question.
But how do you see it going? It's hard to speculate. Is it a continuous change, or is it something that depends on big...
You're the speculator. See, you and I think differently. I think of the possibilities, but I'm afraid to put things in. When I see the dark, I always think of the dark as too big for me to guess at. You see, to guess, it's not much use in guessing particular things. But you're different, and I would like to discuss with you sometime how do you do that, because I'm really a little afraid to make specific guesses.
Is it your background?
I don't know.
The way you kind of grow up.
I don't know. I'm afraid to make specific guesses because the moment I'm making that guess, I can see 7 other alternatives. And so since I see these other alternatives, I don't know which one to piddle with. I don't like to spend a lot of energy on one.
My choice is very simple. I don't set any requirement that the answer be right. It's just what I'm interested to follow.
That's the difference. That's the difference. That's the difference.
Yeah.
Well, I'm trying to find
If I'm interested in...
I'm trying to find out not how nature could be, but how nature is. See, what's right.
Well, I don't think you'll ever find it, you see. I don't think you'll ever find it.
I see. And your idea is to find out what nature could be. Different possibilities.
No. What I think is interesting. Yeah.
Even if it's wrong.
Common ground is enthusiastically explored. But is it only shared experience and knowledge that forms a bond between working scientists and separates them from us, the interested layman, or even the artist? I mean, scientific fields are becoming so specialized and they're so varied. Are you really saying that you have more in common with, say, a paleontologist or someone in a branch of science very far removed from yours than you would with a playwright or a poet?
Absolutely, especially if he's a good paleontologist. Because he's a good paleontologist, he's not just looking at old rocks. He's looking at the history of the Earth. He's looking, when he stands and he looks at his own fingers, and he knows it's got 5 bumps, and he thinks of how did it evolve with 5 bumps. It's got the same as whales, and so on. And we keep talking about the importance of the fact that the thumb opposes. Then we can start discussing, is it really so important that the thumb or is it language that has been evolved, the system of symbols, or the size of the brain? This is a paleontologist. I can talk about this stuff. That's close to his field. Dolphins have bigger brains than we are. They have a signaling system, and you get interested in that, and you start to discuss all that they know about dolphins, and you complain that the way the United States Navy has been doing its experiments is not right, and we ought to find out more about dolphins. And you go on and on. You talk, those are things of the day. They're just as good, but you can go on and on. When I talk to a playwright or something, I find, because I don't go to plays or something, I don't find it easy to talk to them. I don't get much out of it.
I was going to say, this is because you can talk to scientists in other fields, presumably because you read the scientific magazines, presumably, and hear the scientific gossip rather than...
No, because we don't have to have magazines or gossip. We think originally. We think of a new idea. We talk to each other and we try to look at something from a new point of view, and we delight each other in a new point of view. And when you're talking to somebody else who's trying to think of something new, different, and he thinks he's thought about the whales or the dolphins, and he has some little thing he's thought of that's a little different than the thing that you've thought of. And so when you're talking back and forth, he's excited by your point of view about dreams, and you're excited by his little observation that he has made about dreams, if he has happened to have thought about that. So the point is, and our backgrounds give us a slightly different point of view. I mean, a scientific background. Like I specialize in physics, to say he specializes in paleontology. So his information on dreams might be more deeper, more evolutionary. For example, he can't, we don't have a way of telling, I suppose, about the evolution of dreams, but he might know, for example, about other animals. He might have thought about whether other animals dream and what the signs are, and all other things that I hadn't thought of. I can't make it up now because I'm not the paleontologist, but I believe that, yes, I find always that a good man, I take it all back. I take it all back. A good man, I talk to good men in other fields. There's certain kinds of men in every field that I can talk to as well as I can talk to a good scientist. I met a historian, or a writer of history, from France once, and I had a marvelous conversation with him. Maurois, his name was Andre Maurois. And then I met an artist, Robert Irwin, who's a very important artist in Los Angeles in modern art, and I could talk to him at the same depth of excitement. So I take it all back. If you give me the right man in any field, I can talk to him. I know what the condition is, that he did whatever he did as far as he can go, that he studied every aspect of it as far as he has stretched himself to the end. He's not a dilettante in any way. And so he talked deep as far as he can go, and therefore he's up against mysteries all the way around the edge. And awe. And we can talk about mystery and awe. That's what we have in common.
You were talking a bit about these fallow periods when things get very painful.
After discussing working problems, it is natural that Feynman and Hoyle should savour that most thrilling pleasure of all, the moment of revelation.
You try all sorts of things and you're hopeful about trying it. Have you had a moment when, in a complicated problem, where quite suddenly the thing comes into your head and you're almost sure you've got to be right?
Oh, yes.
I mean, this is a great...
Oh, God. Yeah. And then you try to figure out what the conditions were of that moment that you can do it again.
Yeah.
For example, I worked out the theory of helium once and suddenly saw everything. I was struggling for 2 years.
That's right.
And suddenly saw everything.
And
one afternoon, I can remember everything about it, by the way. It's psychologically funny. You can remember the color of the paper you were writing on. Is that true? And the room and everything else. And then you wonder, what's the psychological condition? Well, I know at that particular time, I simply looked up and I said, wait a minute. It can't be quite that difficult. It must be very easy. I'll stand back and I'll just treat it very lightly. I'll just tap it and it'll say boom, boom, and there it was. So how many times since then I'm walking on the beach and I said, well, look, it can't be so complicated. Tap it, tap, nothing happens.
Nothing happens,
So the lights are great, but the secret way, what's the condition?
It's that missing bit in the brain, isn't it?
Right.
That suddenly lights up. And
I have no idea. I've thought about it because some some
You
man
can't
suggested
turn it
that I
off.
think about that. Because if I could only figure out the formula for what condition to be in to get good ideas,
yeah.
I'd be much more efficient and more
Yeah,
happy.
yeah.
You know? So I've often paid attention to what the condition is, and have never found any
No,
correlations
no.
with anything. By the way, it's the delight. It's absolute ecstasy. You
Yeah,
just go
yeah.
absolutely wild.
And how long did it last for?
That drives
How
you.
long does it last for?
Well, it's not very short. It's a very big moment, and then
3
after
days.
That, yeah,
about
and
3
so
days,
on.
yeah.
And then there are lesser pleasures
Yeah,
as you
it's less
see it,
and less,
as you work
yeah,
on
yeah.
more
That's
things,
right,
and more
yeah,
people
yeah.
notice it, and
But
you
the high
talk
peak,
about
you're
it.
on the high peak for about 3 days.
That's right. Yes,
Yeah.
it's like a
Yeah.
supernova, I suppose.
Yes.
No, that's
That's
54
right,
days. That's
yeah.
better.
Yeah.
But I was going to say that it's the hope of that kind of gold
It keeps you going.
that can keep you going through these
Yeah.
doldrums, you
Yeah,
see.
yeah,
And that,
yeah.
I think, what I learned when I was a child from my father was that if you did work a little bit at these things, there would be a time at which you'd get this.
Yeah, yeah, yeah.
And I had to learn that first,
Yes,
or I'd never been
yeah.
able to do it.
Yeah. And then afterwards, you wonder why the devil was I so stupid that I didn't see this.
That's not only true of you, it's true of the history of the science. You can always look at a particular moment in history and wonder why they hadn't thought of it 20 years earlier or 10 years earlier, depending on the case. It's because we're dumb somehow.
It's most mysterious, this. It just means that however good you may get comparatively compared to
Apes
and so on, we're still very bad at it.
Absolutely.
Yeah.
We're doing the best we can. And
Yeah,
ain't
and they're
very
kind of
good.
stumbling.
It isn't very good.
Yeah. This depressing and sobering thought.
Well, it's been fun.